Good afternoon and welcome to KAUST Live. My name is Michelle Ponto and I am the Senior Communications Advisor here at KAUST. I'm here today with Stephen Scott, the Senior Vice President and CTO of Cray. He's here at KAUST for our Global IT Summit. And for those of you who aren't familiar with Cray, Cray is one of the world's leaders when it comes to supercomputers. Thank you for joining us today.
My pleasure.
So as I said, Cray is one of the leaders when it comes to supercomputers. Why have supercomputers and high-performance computing become such an essential part of the research field, and what exactly do they do for the field?
Well, high-performance computing is really the universal scientific instrument. Every single area of science uses high-performance simulation along with theory and experiment to advance their field. If you think about some of the experiments that we'd like to do, say you're an astrophysicist trying to understand stellar evolution. You can't exactly do an experiment on stellar evolution in a laboratory. Or maybe you're looking at very detailed interactions of how a drug could interact with DNA or proteins in a person's body. You can't look at the detailed interactions on a very slow time scale doing experimentation. And so simulation allows you to do things that are too expensive or impossible to do with experiment. And every single area of science uses simulation to model the world, to do virtual experiments, and to help advance the field.
So some of these virtual experiments, they could be simulating earthquakes, they could be, what other kind of things can they do?
Oh, everything from certainly simulating earthquakes, trying to predict extreme weather. So numerical weather prediction is a big use of high-performance computing. Understanding climate change over time, simulating other aspects of the Earth, such as earthquakes or tornadoes. But then materials science, trying to build more effective materials. I'm so sorry, my phone is going off. Trying to build more effective materials. My apologies. Okay. To lighter, stronger materials. Drug design is another area. Building better fuels or better engine design. So jet engine design or even automobile design, trying to model the combustion process inside a car to get more efficient engines. Really every area of industrial design as well as science.
That's incredible. And the supercomputers are getting faster and faster, and the same with in the high processing computer is also getting more advanced. Is it the science that's driving the advancement, or is it the advancement that's driving the science?
Well, really the scientists all have an insatiable appetite. We think about computing in terms of factors of 1,000. People talk about a petaflop, which is doing a 10 to the 15 mathematical operations every second. The current goal is an exaflop, which is 10 to the 18. That's a 1 followed by 18 zeros, that many mathematical calculations every second. And so the scientists have problems that can take advantage of 10 times, 100 times, even 1,000 times more computational power than we have. And so the computing industry is basically driving the technology forward year by year to try to build faster and faster computers. And so it's being gated in large part by integrated circuit technology. If you think about the chips that go inside your home computer, those same sorts of chips are used in very large numbers in supercomputers. So instead of having one microprocessor, we might have 10,000 or 100,000 of those microprocessors. And they're slowly getting faster over time as we are able to fabricate smaller and smaller circuits or transistors onto these chips. But we're starting to come into some fundamental limits. The rate of improvement of the technology has been slowing. And so this is really causing a lot of angst in the computing industry, because if computers stop getting faster at the rate that they have been in the past, we're going to have to figure out other ways to get that performance. And so there's a whole new area of processor design where people are exploring different ways of designing processors to try to get more efficiency, because they're not getting quite as much benefit out of the underlying integrated circuit technology as they have historically.
Okay. So it's like you built it and now they really, 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 really want it.
Yes, people have gotten used to the idea that computers get twice as fast every year or two. And we've had that massive rate of improvement for a number of decades. And so we've gotten a little bit lazy, if you will, expecting computers to continue to get faster. And so it's getting harder and harder to make them faster. And so it's time for us to be a little bit less complacent and really put pencil to paper and try to figure out better ways to design these chips.
Okay. As in your current role, I read that you are helping to find the next generation of supercomputing. What will this next generation look like compared to what's happening today?
Well, for the next 5 or 10 years, we'll see a relatively evolutionary path from where we are today. As I mentioned, the integrated circuit technologies, the rate of improvement is slowing, and so we're exploring some new architectures. One example would be using graphical processing units, GPUs. These are the same things that gamers use in their PCs to draw really fast graphics on the screen for doing video games. But that same technology can be used for doing high-performance computing. So we're seeing some exploration of some new processor technologies. We're seeing some other new interesting technologies that are coming into play in the memory and storage hierarchy. How do we store the data that our computers are working on? So for example, for many years we've used rotating disks, magnetic disks, to store data. And increasingly now we're starting to see using flash memory, the same memory that you might have in your iPhone or Android phone, or the USB memory sticks that we stick into our computers. That uses a different type of media called flash. It's a silicon technology rather than rotating storage, rotating disks. And we're seeing that move into computers to do our storage, which improves the performance. So we're seeing a few technologies like that creep in, but mostly it's an evolutionary path over the next 5 to 10 years. After 10 years, things are going to be a lot tougher because the CMOS technology that we've used, the main technology inside computers that we've been improving over the years, is actually reaching some fundamental limits in about a decade. And so we'll have to have a completely new technology come into play to replace CMOS if we're going to continue the rate of improvement we've enjoyed historically.
Okay. Supercomputers are more than just big data. How do they drive innovation within research, within a nation, within an economy?
Well, I've already talked about how computers and simulation are used to advance science, but if you think about industrial competitiveness, the design of better engines, the design of better fuels, the design of new materials that are stronger or lighter or have other desirable properties, all of these areas can help an economy advance in this very competitive global environment. And so we're seeing more and more countries try to take their supercomputing centers and form partnerships with the local industry so that they can have access to that technology to help drive their, build more efficient cars or better airplanes or design better drugs. And so using that technology for industrial competitiveness is something that's becoming increasingly important.
Okay. You're here specifically for the IT Summit and helping KAUST come up with its next 5-year plan. KAUST does have a supercomputer. It's one of yours.
Yes.
And it's very fast, one of the top 10 in the world. Why is it important that an academic Tier 1 university like KAUST have a supercomputer? What are the benefits of it for the university to have it, and how does it benefit the region?
Well, there are really, I think, 2 ways in which you benefit. The first is just it helps you do better science. It helps you push the boundaries in each of the fields. And KAUST is a world leader as well as a regional leader in terms of the science and the research that's being done here. The other thing it does is because it's such an attractive instrument, again, really the universal scientific instrument, it attracts the best people. The top researchers in the world want to go where the best tools are, and so having a flagship computational capability helps KAUST attract the best and brightest researchers from around the world.
Okay. How will this help the region around KAUST? I know we have done some work with Aramco.
Yes.
How can having a top-tier supercomputer and the plan that you're putting in place, how is this going to really benefit the region and other institutions around the area?
Well, that industrial competitiveness is really the key, and Aramco is a great example of that. They were recently able to run a reservoir simulation with 1 trillion cells. This is absolutely unprecedented, the size and the scale. And as you can model the reservoirs more accurately, you can more efficiently extract the oil from those reservoirs. And so that's just one great example. Other local industries that have similar problems could have partnerships with KAUST, and by doing so, they could get a competitive advantage in their field.
Okay. In your opinion, I know you've been in the meetings all week, where does KAUST need to go to maintain its edge and to maintain, to keep up with what's happening?
Yeah, I think that KAUST has done really an incredible job. I mean, I look at what's been accomplished in the few short years that KAUST has existed, and it's rather mind-boggling. So I think you've got a great team of people in place, and they just need to extend and build on what they've already done. So, you know, from a computational perspective, I think there are ways that they can increase the size of their system, bring in new processing technologies, and really just stay at on the forefront in terms of computational capability. So I don't think that they have to do anything different. I think they really just want to build upon the success that they've had and extend that play.
Okay. Do you think supercomputers will ever just become something that people just have in their house?
Well, the funny thing is that if you look at the computational power on a mobile phone, the one that just went off during our interview, there's more computational power in this phone than there was in the original Cray supercomputers back in the 1970s. And so I forget exactly what the number is, but it's something like 15 years is the average time it takes for the computational power of the #1 system in the world to eventually migrate down to the point where it's in a home PC. So we'll continue to see that. Of course, by the time today's fastest computing, the power of today's fastest computers can be captured in somebody's phone, of course they'll have new supercomputers that are 1,000 or 1,000,000 times faster than those. So hopefully we're not going to see an end to that cycle. We're just going to continue to build faster and faster computers at the high end, and when you make that computer 10 times faster, what it means is now the computer that a small group could buy that maybe only costs, you know, $100,000, that computer is going to be 10 times faster as well. So we'll just continue to see this cycle of technology migrating down all the way to people's phones.
And just one last question. I know supercomputing is used in science a lot. Is there any science that is still waiting for an even faster supercomputer to come out?
Yes, and again, really every single area of science is waiting for a faster computer to come out. And the great thing is that once you build that faster computer, the thing that they're waiting for, they'll have new problems then that they can't solve without a computer 10 times faster than that. So we literally will not see an end to the appetite for faster computers.
It's very exciting because your innovation has to be constant.
It's great. The thing that I love most about working at Cray is working with our customers, because we can build a supercomputer and that in itself doesn't do anything for the world. But what our customers do with these machines is just incredible to watch. They're making the world safer, they're designing better products, they're saving lives. There's a tremendous amount of work now going into trying to understand cancer. In the United States, there's something called the Cancer Moonshot, but there are similar efforts around the world where people are trying to look at cancer mutations and understand at a detailed molecular level how the protein networks and different drugs can interact with those and build customized treatments for different cancers. So you look at that, and it just makes you feel good about what you're doing.
That's a really important point, that it's not just a big fancy machine, it actually is making a difference in the world through the work that it can do.
Exactly.
Okay. Well, thank you very much. That's all the questions I have today. This was great, very insightful. I learned a lot about where it's going, what Cray's vision is, and where just how fast things are going to be in the future.
It's a crazy, fast-paced world, but thanks very much for having me. I enjoyed it.
Thank you.